So the method which will convert a given matrix into a row echelon form is called the Gauss elimination method. So Gauss found out this method. He was solving problems in physics. In fact, he was trying to predict the reappearance of the star called Sirius. Okay. So Sirius star was discovered by people they, when it was rising in the sky, and then it disappeared for a long time. Yeah. Gauss wanted to predict exactly when Sirius is going to reappear in the sky, and he devised his method, Gauss elimination method, to predict the coming of the Sirius. And of course, he used many other techniques, but he found out this Gauss elimination method to solve a problem in celestial mechanics. Okay. But Gauss elimination method was actually known to Chinese. It appears in a Chinese book called the Nine Chapters of Arithmetic. It's a book found in China, and it is almost 1,000 years before Gauss. So in old times, it took time for knowledge to spread. Unlike nowadays, through internet, knowledge spreads very fast. So many civilizations discovered these fundamental algorithms independent of each other. So Gauss elimination method is a fundamental algorithm in linear algebra, but it was known to Chinese long before Gauss discovered it. Okay. So the method converts the coefficient matrix of a system of linear equation into a row echelon form. Well, once you have this matrix in row echelon form, you can solve the system easily. You can tell whether the system is consistent, whether there is a solution, or there are infinitely many solutions, or there is a unique solution. Okay. So let me describe this Gauss elimination method. So this involves two elementary row operations. Okay. So we extract the coefficient matrix, we then construct the augmented matrix, and we apply these row operations. So in that example, I showed you certain row operations which were used to convert the given matrix into row echelon form. We now make it a general algorithm. So these two elementary row operations were performed, interchanging of rows. So remember, there was a zero row in that example, and we pushed the zero row to the bottom, and that was done by two interchanges. Okay. The second row was zero row. We exchanged the third row and second row to push it to the third position, and finally we pushed it to the last position. So this is done. Zero rows can be pushed, that is, zero equations can be pushed to the bottom because they really don't matter. They matter for consistency condition. So by interchanging rows, we can push the zero rows to the bottom. Okay. And exchanging one equation with another really doesn't change the solution. Okay. If you exchange two equations in a system of linear equations, we don't change the solutions at all. Yeah. So interchange of two rows correspond to interchanging two linear equations. The other elementary row operation is addition of a scalar multiple of a row to another row. Yeah. And this also doesn't change the solutions, although it changes the system of equations. It changes the coefficient matrix. So if I add scalar multiple of a row to another, it's like adding a scalar multiple of one linear equation to another linear equation. And it's clear that these two system of linear equations have exactly the same set of solutions. But by doing this row operation, these are called elementary row operations, PROs, we can convert the coefficient matrix into row echelon form. And we will need one more condition, one more elementary row operation, namely multiplication of a row by a non-zero scalar. Okay. And we use this operation in the example that I showed. We multiplied one row with 2 and added 2 times one row to another row, or added 3 times one row to another row. Okay. So these are the 3 elementary row operations. Interchanging 2 rows, which corresponds to interchanging the 2 linear equations in a system of linear equation, adding a scalar multiple of a row to another row, multiplying a row by a non-zero scalar. So if I have many linear equations, if I multiply a linear equation, one of the linear equations by a non-zero scalar, yeah, then it is not going to change the solutions at all. If I had a solution before, I substitute the solution after multiplying an equation by a non-zero scalar, it will continue to remain the solution, and vice versa. So these 3 elementary row operations, they do not change the solutions of the system of equations. And so we can apply these to the coefficient matrix or the augmented matrix, and you will see that the Gauss elimination method, by using these 3 row operations, can convert a given matrix into row echelon form. Okay, yeah. So the augmented matrix AB is transformed into another augmented matrix A prime B prime by EROs, and AX equal to B if and only if A prime X equal to B prime for all X. So AX equal to B and A prime X equal to B prime, they have same set of solutions, because interchanging 2 rows amounts to interchanging 2 equations. Multiplying a row by a non-zero scalar amounts to multiplying a linear equation by a non-zero real number, and we can add a scalar multiple of one linear equation to another, that also doesn't change. Okay, so if we transform a augmented matrix of a system of linear equations by using these 3 elementary row operations, we keep on getting new matrices, and the corresponding solutions are one and the same. Okay, right? Yeah. So, so we are justified in performing elementary row operations on the augmented matrix in order to obtain all solutions of a given system. Okay, transformation of A to REF. Okay, let me explain that. So this is a definite procedure. It is an algorithm. It's like a program. Okay, it's a definite algorithm which will convert any matrix into row echelon form. So what are the steps? So pick a m by n matrix and assume that it has real entries. This algorithm can be applied on matrices with complex entries or rational entries. Okay, it doesn't matter. So for simplicity, I am assuming that A is a real matrix, although it can be applied to matrices with rational entries or complex entries. If the matrix is 0 matrix, there is nothing to do. It's already in row echelon form. Okay, right? All the conditions of row echelon form are met by the 0 matrix. This is the trivial case of a matrix in row echelon form. So we assume that the matrix is a non-zero matrix. Yeah. So if it is non-zero matrix, then we start scanning the column vectors. Okay, we start scanning the column vectors. The fact that it's a non-zero matrix, it means that there is a non-zero column. Yeah, there is a non-zero column and there is a non-zero row. So look at the first column, which is non-zero column from the left. Yeah, start scanning the first column, second column, third column, etc., until you hit the first non-zero column. And suppose that is the K1 column. Yeah, so let K1 column K1 be the first non-zero column of A. Yeah, and so since it's a non-zero column, it has a non-zero entry. That non-zero entry is sitting in certain row. Yeah, that non-zero entry is sitting in certain row, and all the columns before this are 0 columns. So as soon as you encounter the first non-zero entry in this non-zero column, that is a pivotal entry, and this column is a pivotal column. Yeah, because all entries below this first non-zero entry in this first non-zero column, they are all 0. So as soon as you encounter the first non-zero column from left, and then you go down and find out the first non-zero entry in this first non-zero column, that is bound to be a pivot of the matrix. Okay, so let column K1 be the first non-zero column of A, and let some non-zero entry P1 in this column vector be the jth row. Suppose that non-zero entry occurs in the jth row. Now interchange the row j with row 1. Yeah. So we scanned all the entries of the K1 column and encountered that the first non-zero entry in this K1 column occurs in the jth row. We will interchange first row with the jth row. Okay. So this is a definite algorithm. So we want all the zero rows at the bottom. So we are doing that. Okay. So this jth row becomes the first row, and by converting into the first row, by interchanging the first row with the jth row, I have made this non-zero entry into a pivotal entry. So the first row will have a pivot. We want the first row to have a pivot. We want the second row to be a pivot, etc., etc. All the zero rows should be at the bottom. Okay. Yeah. So A is transformed into this A prime. Okay. So you see that a first few columns of A prime are 0, and this yellow entry P1, this P1 was actually sitting inside the jth row. Yeah, it was sitting in the first non-zero column. Is this column in which P1 entry is occurring? Okay, the yellow entry is occurring, and it was earlier occurring in A in the jth row. I interchanged jth row with the first row. So then this P1 becomes the pivot, first pivot in the first row. It's a pivotal entry. Yeah. So now we repeat this process. P1 becomes the chosen pivot in row 1. I forget row 1 now. I forget all the zero columns, the first few zero columns of A prime. And now you focus on the remaining matrix. Okay. So forget the first row, forget all the zero columns, and forget the column in which P1 is occurring. Now I get a smaller matrix and repeat this procedure. Is that clear? Yeah, we just repeat. This is the first step of Gauss elimination method, and then we keep on repeating on smaller matrix, and it will lead to a row echelon form. Yeah. So since P1 is not 0, we can now add a suitable scalar multiple of row 1 to A prime to row 2, row 3, etc., etc., so that and all the entries in the column K1 below the pivot P1 are 0. So look at the entries below P1. Yeah, some of these entries could be 0. We can make them 0 by multiplying the first row by a suitable scalar and then subtracting from that row, so that all the entries below P1 become 0. So by elementary row operations, I can convert the entries below P1 into zeros, and that is the condition, yeah, for a pivot, that all the entries below the pivot have to be 0, because the second pivot is going to be to the right of first pivot. We cannot have a non-zero entry below a pivot. So all the entries below P1 have to be converted into 0 entries by elementary row operations, and we can do that. So when you do this, the first 0 columns, there is no effect on them. They will continue to remain 0 columns by these row operations, which are converting all the entries below P1 into zeros. Okay, so this is the step for obtaining the first pivot P1. Yeah. Then we arrive at this A double prime, and now forget the first K1 columns and the first row. I get a smaller matrix, and this smaller matrix, we repeat the procedure. Keep row 1 of A double prime intact. Repeat the above process for the remaining m-1 cross n submatrix of A double prime, and we then repeat. We get this another pivot P2, and all the entries below pivot P2 have to be converted into 0. So after locating my first pivot P1 and converting all entries below P1 into 0, I might encounter certain 0 columns. Yeah, after that. Yeah. So we have to forget those and we repeat the same procedure to locate the second pivot P2 and convert all the entries below P2 by elementary row operations into zeros and keep doing this. Yeah, and so P2 becomes the chosen pivot in row 2, and we keep repeating this process, resulting m by n matrix in row echelon form with P1, P2, PR in columns K1, KR, and the last m minus r rows are 0 rows, because number of non-zero rows is number of pivots. This is the notation. Ri for Gauss elimination method has these row operations. Ri interchange with Rj. So we write this double arrow, I is not equal to 0. Then Ri plus alpha Rj denotes the addition of alpha times jth row add to Ri. Yeah? So Ri plus alpha Rj means Ri is changing. We are adding alpha times Rj to. So the question, what is the question? Somebody is asking question. Yes. What is the question? Can you repeat?
Can we use the combination of
combination of row and
can we use the combination of row and column operation to achieve REF?
No, I did not bring in any column operations. See, if you do column operations, we may change the solutions. Only when you interchange equations or add a multiple of an equation to another equation, you don't change the solution. But when you do interchange columns, then you are interchanging variables. Okay, so solutions will change. So we are not applying any column operation. Okay. Yeah. So the Gauss elimination method involves only the row operations, and it involves those 3 elementary row operations. So far, I used only 2 operations. I didn't use the third operation. Okay. So this will lead. It's clear that this algorithm will terminate, and we will get a row echelon form at the end. And to write down precisely what we are doing, we will follow this notation: Ri interchange with Rj, then adding alpha times jth row to the Ri row. Yeah.